Hello, Dr. Marcia Tuft here, and it is week number 4 of the Great 2020 STEM Summer Camp series. This week, we are doing the Egg Drop Challenge, and I'm recording this on a Zoom call just in case I have problems with Facebook Live. So if you're joining me live on June the 26th, you'll get the same content. But I just want to make sure I've got everything rolling in case I've got any problems. So we are going to learn about impact damage this week. But first, let me talk a little bit about GE Volunteers and Girl Scouts Year of the Girl Summer Camp. I've been volunteering with GE Volunteers and Girl Scouts of Western Ohio since we started the summer camp back in 2016. So this is our 5th year, and we've had a lot of fun experiments. We wish we could be with you live at Camp Butterworth, but since we can't, we're bringing you these experiments virtually. So we hope you're having a great summer, and we hope you're having some fun with these experiments. Let me tell you a little bit about myself. I'm a retired engineer from GE Aviation. I've got degrees in mechanical, aerospace, and materials engineering. I actually did my PhD in materials engineering, and I actually studied the effect of shot peening on metal surfaces, which is basically hitting metal pieces with tiny, tiny pieces of shot. Impact velocity, impact damage, I got to shoot some cool stuff. Anyway, bottom line is I learned some things about impact damage, which I'm going to be able to share with you. So you couldn't have a better host for an egg drop challenge than me. So, but before we get going, some basic ground rules. This is a pretty easy experiment, but you can take it as far as you want to go. You are going to need some eggs, okay? They can be raw, fresh eggs, or you can hard boil them. Okay, number one criteria though, please bag your eggs. So this will make the cleanup a whole lot easier in case your egg protection system doesn't work. So we're gonna bag our eggs in a little ziplock baggie, like this. Okay, I'm just gonna go ahead and bag a few because I plan on breaking at least one. I want to have another one ready to go. And you can still get all the cool data. If you looked at my handout, you will see that I actually showed the fracture surfaces of the eggs. In fact, that's the one cool thing about a Zoom call, is that I can share screen. Okay, so here is a good egg right here. Let's see if this is working. No cracks. No cracks. After I drop it, well, you'll see, because I'm going to do this live. You're going to see there are cracks, and they tend to go in a circle around the egg from the center of the impact site. So wherever the egg lands, the cracks radiate from that impact location. But the cool thing is, I did the same experiment with a hard-boiled egg, and except from completely shattering the egg because you had a liquid inside, it stayed intact, but I got very similar damage. So a hard-boiled egg is a good test dummy if you don't want to use a real egg. So I will let you use either a raw egg or hard-boiled egg. Either way, bag your egg because it's going to be super easy to eat your hard-boiled egg after you break it. You're just helping yourself remove that shell, okay? So you may never do an omelet the same way again after you do your egg drop challenge, okay? So that's the first thing you need. You need your eggs. Then I've got 3 categories for you. So you can do a container category where you put some padding around your egg in a container and let it drop. Or you can think outside the box, okay, and maybe build some sort of a frame and suspend your egg. Or maybe you can get even crazier and come up with some sort of a hang glider system. But we'll talk about those kind of options in a minute. First of all, let's do a really cool, I'm just going to use popcorn for my first second test. Okay, so I'm going to put some popcorn in a bowl, kind of like styrofoam peanut so you can eat it. So if I take a container and I put some popcorn in the bottom, this will act like padding. Okay. Okay, so now I'm going to take one of my eggs, put it into my container. Okay, now I do want to make sure that I've got some padding around the container. And you might have to experiment with, okay, how well do I need to pack this? Can I really get my egg protected on all the sides? How much, it doesn't matter if it's loosely packed or if it's well packed. Oops, that's a little bit overstuffed. I'm not going to get my lid on. Okay, so I got to be able to fit my lid on. In fact, a system like this, I recommend that you duct tape or just somehow secure your container lid. A plastic container like this works pretty well. Okay, so I'm just gonna secure my lid. Okay, now I've got one system. Okay, so first of all, let's see if this system works. Okay, let's see if I've got it in. Okay, so if I got the angle about right, you'll be able to see this fall on the ground. Let's check it out. This is going to be about 7 feet. I'm trying. Ready, steady, bombs away. Whoops, that landed on its side. Let's see if my egg survived. Did I have enough padding? So now, and it looks like I have a successful egg test. Woohoo! I do. Look at that. Okay, it's sweaty because I took it out of the refrigerator and it's warm outside, okay? But that system worked. So what other things might work? Paper towels, crumpled paper. Okay, maybe you think, oh, she didn't need all that protection. Well, what do you think would happen if we just dropped it in a container without padding? This is what we call a test case. Now, one of the things you need to know for your egg drop challenge, you need to be dropping this egg onto a flat, hard surface. This is a concrete patio, hardwood floor, pergo, tile. That would work. Carpet, grass, no. They're going to provide some cushion. Okay, so now we're going to do test number 2, just as a control. Is a container, did I need that popcorn, or is this container enough? Let's give it a try. Ready, steady, bombs away. Oh, nope, we very clearly did not have a winner here. Okay. So we've proven that our surface is hard enough to break an egg. But can we learn something about damage? What are the aspects that are going to protect this egg? How can we design a system? What are going to be the good things we should take a look at? Well, I want to talk, okay, and for the younger girls, feel free to just go experiment however you want. So let's try a couple experiments real quick. What would happen, do you think, if I just dropped the egg from like an inch above the ground? Or let's see, what if I put it onto a soft surface? Let's try a soft surface. Okay, soft surface, can you see that? Okay, let's get you a little bit closer. chair in the way. Okay. So soft surface, a couple inches from the ground. Ready, steady, go. No damage. Okay. So that surface provided some cushioning. What about the same height without the cushioning? Okay, I heard a crack there. So you saw how much damage we had from like 7 feet, 8 feet tall. Okay, so this is all the damage. Lots of cracks around there. And I could wash this off and show it to you a little bit better. This egg, just a couple inches above the ground. I don't know if you can see that. So you got a small crack. The egg's not even leaking out yet. Okay, but you got right where it hit, you've got the circular impact damage. Okay, so engineers call guesses a hypothesis. It's a fancy name. It makes us sound like we're earning our money, right? We earned our college degree. A hypothesis is just a guess. So if I were to guess, I would say dropping from 8 feet high causes a whole lot more damage than dropping from 2 inches off the ground. The egg's the same. The surface is the same, but the damage is less severe. So what are some things that we could do to reduce the damage from impact? Well, let's think about that, huh? I'm going to talk to you for a couple minutes about potential energy and kinetic energy. So bear with me. These are terms you might not have heard of. Okay, so potential energy is stored energy. So if I take something like this exercise ball and I lift it up, I'm putting energy into this ball to lift it up. Potential energy is a function of the mass m, the gravitational constant g, and the height I lifted above the ground. So if I only lift it a couple inches above the ground, I don't put as much energy as if I lift it 7 feet. Okay, so that's potential energy. Now, when I drop the egg for the egg drop challenge, I put potential energy in the system because I'm raising it to about 7 or 8 feet high. I'm storing that energy. But when I release it, when I drop it, I'm converting that into kinetic energy. Kinetic simply means moving. So moving energy, kinetic energy, is equal to 1/2 times the mass. So this is a fairly heavy exercise ball. 1/2 times the mass times the velocity squared. Okay, so velocity squared, that means just velocity times velocity. So velocity, really important. Okay, so that's kinetic energy. Now, momentum's related to damage. Momentum is a function of mass times velocity. If I raise my ball up 7 feet high, whatever, I put all this potential energy in it, the kinetic energy is 0. If I let it go, right before it hits the ground, it has a kinetic energy equal to 1/2 mv squared. So potential energy is mgh, kinetic energy is 0 at station 1 here. At station 2, potential energy is 0, but kinetic energy is 1/2 mv squared. Gibberish, gibberish, gibberish. What it boils down to is that I can solve for velocity as a function of the gravitational constant and height. Does that make sense? Does that mean, hey, if I did that right, that the velocity of this ball and this tiny, teeny little bouncy ball would be the same if I drop them from the same height? That doesn't seem right, does it? Well, let's test it out. That's what we engineers do. Okay, so the best that I can do, we're going to do this drop test. And we're going to see which ball hits the ground first. What do you think gonna hit the ground first? The heavy exercise ball or this little weight, this little bouncy ball? Which is going to hit the ground first? Let's give it a try. Nearest that I can do. Ready, steady, go! Well, as near as I could do it, as accurately as I could do it, they hit the ground at the same time. So that says that I got my math right. And velocity is a function of the drop height. Ooh, so that means when we broke our little egg, which one is it? Yeah, when we did our little egg from, I'm having problems finding it now. Here it is. When we did our little egg from 2 inches, we should have seen less damage, and we did. When we dropped it from 7 or 8 feet, we saw a lot of damage. That's exactly what we would have expected from this relationship. So, okay, now let's talk about damage for a minute. Damage is a function of mass times velocity. And the velocity is a function of the drop height. Okay, what can I do to reduce damage? And where does all that energy, okay, when you splat something, where does all that energy go? You might have heard something, conservation of energy, conservation of momentum. Well, conservation of energy means that, okay, if I didn't get it back in kinetic energy, I didn't get it back in potential energy, where did that energy go? Well, we heard an impact, right? So some of the energy went into sound. Some of the energy went into heat. You may not know this, but heat is stored in vibrations. So living matter, anything that's above absolute zero is vibrating. And the hotter it is, the more those molecules and atoms are vibrating. So when you think about it, if I hit my hand, ooh, I feel a little bit of heat when I smack that hand. And that's because impact is heat. Okay, so some of it went into heat. Where did the rest of it go? Well, creating fracture surfaces. So making all those cracks, that absorbs energy. So when I used my popcorn, I couldn't tell. I mean, it's all crinkly anyhow, but my popcorn could have deformed a little bit and absorbed some of the impact damage energy. So that's what your panning is going to do. Your panning is going to absorb some of that impact damage and deform a little bit. So that's what panning does. It dissipates energy and hopefully protects your precious breakables. Okay, so that's a little bit about momentum and damage. So I have one other digression right now I want to take you on. All right. These two, well, actually 2 little digressions, okay? These 2 things hit at the same time. Do they do the same amount of damage when they hit? So this is a lot heavier than this little bouncy ball. Will they do the same amount of damage? Any guesses? Let's test it out. I have, for this part of the experiment, I have a little bit of a cardboard box here. Okay. It's not special reinforced cardboard, it's just a box. Okay, so for the first experiment, I'm going to drop this bouncy ball. Okay, I actually have to aim, so I'm not going to be able to get it to 7 or 8 feet high because I can't aim that well. Okay, and now I'm going to try with this one. So which one do you think is going to do the most damage? The little bouncy ball or the same? The velocity is going to be the same when they hit if I can get it from the same drop height. Let's think about that. Okay, can we see that? I'm going to focus the camera just a little bit more. Okay, let's give this a try. Okay, bouncy ball. Oops, I got to get this. I got to be a little bit closer. Bouncy ball, ready, steady. Woohoo, go. Okay, so the box moved a little bit, but no damage. No observable damage, okay? Same experiment. Heavier ball. Are we ready? Ready, steady, bombs away. Whoa, okay, I didn't even hit it square on. And I smashed that thing. Okay, so clearly, if I go back to damage, and I'm thinking, mass times velocity is related to momentum and damage. And there are different regimes of damage depending on how fast you're going. So this may not be the perfect relationship for every impact. But clearly the velocity was the same. I did a whole lot more. I had a whole lot more momentum with the bigger mass, bigger weight. So I did more damage. So looking at momentum as a predictor of damage, that looks pretty good. So I can look at mass and I can look at velocity. I have one more little digression. Okay, in a perfect world, ideal system, no secondary factors, we got it. What happens with this little bubble wrap envelope, do you think? Will this fall through? Let's do balls here. So we had a heavy ball and a light ball. They hit the ground at the same time with the same velocity. Okay, height translated to velocity. What do you think will happen? Will the same relationship hold with our bubble wrap envelope? Which do you think is going to hit the ground first? Same thing applies? Well, I'm an engineer, so let's test it out. Okay, here goes. Ready, steady, bombs away. Okay. Gee, Newton let me down. The bubble wrap wafted around. It didn't fall as quickly. So that probably means the velocity of the bubble wrap wasn't the same. Because, let's see, velocity times time gives me distance. So if the distance was the same, the time was a lot longer for this. That meant the velocity needed to be a lot slower. So why do you think that was? Well, any guesses? Do you agree that this had a slower velocity? It took longer to hit the ground, so it was a lot slower. Shape, air resistance. This is so light and so flat that air was able to delay the descent. I'm not sure about this thing. The box, nope, the box is clunky enough, it hit, but this, the shape delayed. Okay, so I've got 3 categories of egg drop challenge. The container, as I mentioned, the outside of the box. And if you want to get really funky and creative, try to do a hang glider or a parachute system. See if you can lower that velocity directly. Okay, so before I go to the next experiment, I want to talk about mass, springs, and dampers, the 3 main elements of a mechanical system. Okay, so my mass. This is the easy one. The mass is our egg or our big weight ball, fitness ball, okay? The force acting on a mass is proportional to the acceleration acting on it. So on Earth, the gravitational constant for Earth. If you're on the moon, what would be the difference between the weight of this thing on Earth? No, first question, what's the difference between the mass of this ball on the Earth and the moon? Any guesses? So mass, the forces acting on mass are equal to the mass times the acceleration, which in this case on Earth would be the gravitation for Earth. On the moon, it would be the gravitation for the moon. The mass is the same. But if I asked you the weight is actually this force thing. So the weight is equal to mass times the gravitational constant. So the mass of this is the same on the Earth and on the moon, but the weight would be different because gravity is different on the Earth and the moon. Okay, so those are the forces acting on a mass, and we saw how we could put energy into it by lifting it. and convert it to kinetic energy by dropping it. So that's what masses behave like. Okay, springs, ha ha ha, like a rubber band. Springs store energy by deformation. So if I stretch this spring, this rubber band, I've put potential energy in it. That's a function of the spring constant, which you don't know, and the elongation, which I can measure. Okay, so if I let it go, whoops, that didn't work. Woo, okay, and I just converted that rubber band potential energy into velocity energy, into kinetic energy. Okay, so the force in the spring is equal to the spring constant times the amount that I stretch it. Okay, so delta x distance is actually equal to velocity times delta time. So I can get to velocity that way. Typically time is going to be really short duration. So velocity is not going to have a big impact on what force a rubber band is going to absorb. It's more the elongation. So we tend to think of springs as storing and releasing energy. They're energy storage devices. Okay, the third type is a damper. So dampers, an example is this pillow. Dampers actually dissipate energy. They always act opposite the applied force. So if I put a force that's equal to this mg on this pillow damper here, the damper is going to resist with an amount that's negative b, b being the damping coefficient, times the velocity. So dampers actually act on velocity. So the slower something hits a damper, the less force it exerts. The faster something hits, the more it resists. So let's take a look at a damper. If I can find my big, oh, heavy ball. Okay, so we're gonna put a damper here. Oops. Okay, and did you see that deformation? The damper absorbed and cushioned that impact. So if you're designing an egg protection system, what do you think is going to be a better protection system? A rubber band that stores and releases energy, or a damper like my pillow? Let's give it a try. Okay, now I got to warn you, it's possible to survive the initial impact and still roll off and crack on the concrete. Okay, we're dropping our egg onto the pillow. And it landed. Woohoo! It stuck the landing. No damage. Not a bit. A successful test. Okay, so a damper is a great element and something you want to include in your packaging system. In fact, most of our packaging comes into the category of dampers. Okay, but I have some extra wonky, funny egg drop systems that I'm going to share with you. Okay, this is the extra caca. This one I made a week or so ago, and another free lesson for you. A structure. This is not a structure. Triangles make good structures. And all the spring energy acting on this rubber, on this frame, and the elasticity of the joints here have allowed this frame to deflect. I think I might actually have to reinforce a couple of these before we go. So some of these systems you might design may not survive intact after a day. I just thought it would be fun. I have some bamboo to play around with. And it's a spring-based damper. So I'm gonna put my bagged egg into my little suspension system. See if I can close that. Okay, so this is the really caca outside the box frame number 1. So let's test it just for fun. Grins and giggles. Okay. Ready, steady, go. Ooh. Well, so this may be a spring-based system, but there's a lot of damping going on in these joints. And if you check out my videos, you'll see that when I tested this enough times, I eventually got it to land on its side and it broke. Now here's another one. Let's try this. I have never tested this one before. This is a much sturdier system. It's made from Connects. You can see that. It's made from Connects and it's got some rubber bands. So all I did is I took a little Ziploc bag, punched some holes in the corners, fed some rubber bands through and wrapped it around the Connects. Kind of suspend it. Okay. So let's give this a test. Okay, now what do you think it's going to do? You think we're going to have a successful test here? You know, this thing can bounce around. These rubber bands can deflect. So is this a snug enough system, suspension system, to protect our egg? I have no idea, but I'm an engineer, so I'm going to test it. Okay, here goes. Ready, steady, bombs away. Whoops. And my Connects popped out. So you see, that's another example. Energy being dissipated. Ooh. I think I've got a crack. So energy was dissipated when that corner popped out. And yes, my egg cracked. So it looks like I was right. If I want to protect my mass from breaking, I'm better off finding a damping element. Or maybe finding another way to lower the velocity. But this system didn't do it, but it was fun trying. I can't wait to see what experiments you come up with and how they turn out. And I hope you'll post a photo or a video of your egg drop experiment on the Girl Scouts of Western Ohio website. I also invite you to visit my website, putneydesigns.com, and on the egg drop page, if you're willing to load a photo or video, you'll be entered in a contest to win a free autographed copy of my book, Putney and the Magic iPad. So please do that. If you are under 13, you will need a parent or a guardian to submit that entry on your behalf. But I would love to welcome you to my website. And there's also 2020 summer camp, STEM summer camp schedule there. So you can check out all the experiments we've got planned for the rest of the summer with links to the basic video demos and handouts so that you know what's coming. So I hope you will check it out, and I hope you have an absolutely fantastic summer. Thank you for joining me with the Great Egg Drop Challenge. I hope you had fun. I sure did. See you next week. So next week is going to be build a cardboard catapult, and you're also welcome to design your cardboard catapult, decorate it to make it pretty. This is Dr. Marcia Tuft signing off.